So now let's look at the work done by a variable force. Work can be calculated by finding the area underneath a plot of the applied force in the direction of the displacement vector versus the displacement itself. So as an example, if we were to find the work done by a variable force, what we would do is we would plot the variable force versus the displacement it corresponds to on an XY graph, where your displacement vector goes on the x-axis and your force vectors go on the y-axis. So how do we find the work? Well, we can find the work by figuring out the area under the curve. This is a rectangle, so the work done is going to be the length times the width. So the length of this vector is going to be the displacement, which is x1 minus 0, and the width of this is going to be f1. Work done by f2 is going to be the length times the width, which is x2 minus x1 and f2. Similarly, work done by F3 is going to be given by x3 minus x2 times the F3, which is the variable force. Now you can make these rectangles as big as you want or as small as you want, depending on what your force is. So the total force is then going to be W1 plus W2 plus W3. Example 2. An ideal spring has K equals 20 newtons per meters. What is the amount of work done by an external agent to stretch the spring 0.4 meters from its relaxant? So in this case, what you're going to do is you are going to plot X versus Fn, and you're going to plot them knowing the value of K and keep going on from there. So the area under the curve for this guy will be 1/2 kx1 and x1, which is given by 1/2 kx squared, and you plug in the numbers and you come up with 1.6 joules. Now this is a very good thing that will lead us into talking about Hooke's law. So for springs, we need to use something called the Hooke's law, and Hooke's law says that hanging masses on a spring, we find that the stretch of the spring is directly proportional to the applied force. This is what is known as the Hooke's law. For an ideal spring, F equals minus kx, where Fx is the magnitude of the force exerted by the free end of the spring, x is the measured stretch of the spring, and k is the spring constant. The larger value of k implies that we have a stiffer spring. So now let's look at a problem. If the forces of 5 newtons applied to each end of the spring causes the spring to stretch 3.5 centimeters from its relaxed length, how far does a force of 7 newton cause the same spring to stretch? And part B says, what is the spring constant of this spring? So what do I know? I know F equals kx. That means as I apply different forces, my x value changes. However, my spring constant for any spring remains the same. So F1 should equals kx1. So any force that results in any displacement equals x2. And then F2, which is a different force, will result in a different stretch. However, the values of k will remain exactly the same. So this implies I can rewrite F1 over x1 as k, and this I can write F2 over x2 as k. So from this and this, since the k's are the same, I can rewrite F1 over x1 equals F2 over x2. Recall or remember that the value of k will not change for any spring. So now it says, now I come back to my question, and it says that forces of 5 newton causes my spring to stretch 3.5 centimeters. And how far does the force of 7 newton stretch the spring? So I have all the other terms except for x2. So I do a little bit of algebra, move things around, divided by 5 newtons. So this is also in newtons. Newtons go away, and I come up with an answer in centimeters. And my answer comes out to be 4.9 centimeters, but you better confirm that and make sure that it's actually true. Now, part B of this question says, what is the spring constant of this spring? Well, all I need to do part B of this question is to look at this. I know F1 equals Kx1. So F1 that was given to me was 5 newtons, and X3 that was given to me was X1 was given as 3.5 centimeters. Now the idea is I could leave it as in centimeters or I could convert it to meters. It's your choice. But basically you will get something like 3.5 centimeters. If I want to convert it to meters, it will be 0.035, and that should come up with a value of K. So the value of K for this problem will be newtons per meters. And my answer comes out to be 1.43 maybe newtons per meters. So now this problem says calculate the spring constant for a spring that stretches 5 centimeters from its equilibrium point when you add 5 kilogram mass to it. So as always, I am going to start with my free body diagram, or at least draw my diagram, okay? And what it says is that it stretches, so with my mass that's attached to it, it is 5 kilograms, and it stretches at a distance of 5 centimeters, okay? So what will the spring constant be? So I know if I draw my free body diagram, my weight is acting downwards, right? And my force is acting upwards. So my net force in the y direction will be F minus mg, which is the weight acting downwards. So sigma Fy, is it going anywhere? Is it doing anything? No, it's just hanging out. So that means sigma Fy will equal to 0. And I am left with F of the spring equals mg. Hooke's law says F equals Kx, which is equals to mg, which means I can convert this to meters, 0.05 meters, and this is going to be Kx equals mg. So I know, what do they give me? They give me 0.05 meters is what the stretch is, and I have a 5 kilogram mass, and then I have 9.8 as my value of g. So all I have to do is move things around, 0.05 and 0.05. This gets canceled, and I can have the value of k be equals to k times 9.8 divided by 0.05 comes out to be 980 newtons per meter.